Once again, welcome to waidusmacademy. Today we are looking at continuing the science paper for Cambridge Checkpoint, and we in our previous video we did question 1 to 7. Today we're going to do question 8 to probably to, if possible, to the end. Okay, here is your periodic table, okay, for you to use. So we're going to look at the remaining questions, question 8 to 10, right? So without much ado, let's begin. The first question is chemistry. This question is chemistry. Say, Perry investigate the reaction between lumps of zinc and dilute hydrochloric acid. Lumps of zinc and dilute hydrochloric acid. So zinc lump is solid. Okay, the lump of zinc is solid, right? So he investigated the distance between the lumps of zinc and dilute hydrochloric acid. Now here you have the zinc, the lumps in solid form. The lumps of zinc, these ones, and then the dilute acid is this liquid, this aqueous. So the dilute acid will be eating the lumps of zinc till you find a different thing. And Perry finds that the reaction is faster if he heats the dilute hydrochloric acid. So if he heat this acid, the rate at which this one will melt or this one will change from being lumps to solution form is faster. Now explain why using the particle model. Why is it faster? Okay. Explain why the rate of reaction is faster when using the particle model. Okay, so if you heat it, if you increase the temperature of the acid, that means you heat the acid, you will have this one is able to the heated acid is able to melt the lumps as fast as possible, faster. So hot acid breaks the particle faster. Break the bond faster. The bond of the zinc molecule faster. Breaks the bond of zinc molecule faster. Zinc atoms faster. Okay, hot acid breaks the bond of the zinc atom faster. This is evident from temperature, the effect of temperature. Okay, increasing temperature increases rate of reaction. Increase temperature, increase the rate of a chemical reaction. Increasing temperature increases the rate of chemical reaction. So we say increasing temperature increases the rate of reaction. Increase the rate of collision. Temperature increases the rate of collision, hence the rate of chemical reaction. It increases the rate of collision of the particles. Increases the rate. Take this is 2, we reduce the size. Increases the rate. The rate of collision. Rate of collision of particles. Of particles. Okay, so if this one becomes hot, it's easy to melt the lump. Okay, the rate of melting is higher, and so on and so forth. So whatever within that scope, you get your marks. Now Perry wants to make the reaction go faster. So if he wants to make the reaction go faster, one of the things he can do is to put this in powder form. This lump, you break down the lumps, this lump zinc, and put it in fast powder form. It will definitely increase the rate of reaction. So he wants to make the reaction go faster. He does not want to change the volume of the dilute hydrochloric acid. He doesn't want to change the volume, meaning he don't want to either reduce the acid or increase the acid. He doesn't want to change the temperature of the dilute hydrochloric acid. He don't want to increase it any further. And he does not want to change the mass of the zinc, meaning he don't want to either reduce the quantity of zinc or to increase the quantity of zinc. So what? Describe one other way that Perry can make the reaction go faster. Okay? Powder. Make the lump in powder form. Make the zinc lump in powder form. Increase the surface area. Okay? Make it the zinc lump. Make it the lump of zinc in powder form. Grind it. Grind the lump of zinc. Because reaction will be faster if you increase the surface area. Okay, making the lump of zinc in powder form. The lump of zinc if you don't want to increase temperature and you don't want to increase volume and you don't want to increase the mass, but you want to increase the rate of reaction, then you should increase the surface area of the substance. Making the lump of zinc in powder form. Powder form. If you put it in powder form, you increase the surface area, and hence you increase the rate of reaction. Okay? Now we go to the next one. Perry wants to measure the volume of the gas given off during the reaction. He wants to measure the volume of the gas given off during the reaction. Complete the diagram of the equipment Perry uses to collect and measure the volume of the gas. Okay, you connect this one to a syringe. You can connect this one to a syringe. Okay, or you connect to a cylinder. But in this case, I think syringe will be better to measure the volume. So you connect this one to a syringe. You calibrate it from one side. Okay, let's assume here. Okay, let's assume here is 0, here is 10, here is 20, here is 30, here is 40, here is 50, and here 60. So the the volume will be measured over here. So you just do something like this and you get this marks. And let's move to the next one. Perry does a risk assessment on his investigation. He decides to wear safety goggles. Now, why does he decide to wear safety goggles? To avoid acid splashing to his eyes, to avoid eyes contact with the acid, contact or hot acid. To avoid, you remember he heated the dilute hydrochloric acid and it become hot. To avoid eye contact with the hot acid. Eye contact. To avoid eye contact with the hot acid. Okay, this is like alternative to practical in either paper 6 of chemistry or paper 6 of biology. To avoid, or physics. To avoid eye contact with the hot dilute hydrochloric acid. With the hot with the hot hydrochloric acid. Hydrochloric with the hot hydrochloric acid. Okay, so that's that. We're done with question 8. Now we go to question 9. Xavier investigates the current in a circuit containing two identical lamps. Two lamps. Okay, this is an ammeter. A means ammeter 1, measuring the current coming from here. This is the positive side of this cell. This is like a cell because it's just one unit. This is the negative side. So current flow from the positive here into the circuit. When the current gets here, it splits. Part of the current goes through this branch. The other part of the remaining current goes through this branch. This ammeter A2 is to measure the current in this bulb. This is a bulb. This is a bulb. This is a bulb. A means ammeter, the instrument for measuring current. This one is like wire, Current flows in this wire. We connect in series. We connect an ammeter to measure the current coming from here. When the current gets to this junction at point X, it splits into two. Part of the current flows through this branch. Another remaining part of the current goes through this other branch. And there's an ammeter here to measure the amount of current that enters this branch. Another ammeter here, A3, to measure the amount of current that enters this branch. And then the two currents, they meet up again, they sum up again, and it is being measured by A4. A4 is usually equal to A1 because the current that leaves sums up becomes the same value as it was before it got to the junction. So A4 and A1 is usually the same value, but here the values are different. The current splits up when it gets here. Now let's see what the question is going to look like. Okay, this direction of current flow, like I already explained that because it's coming from the positive side, conventional current. Okay, now she changes the number of cells. This is a cell. This is a cell. She can make it 2, 3, and so on. Change the number of cells and measure the current A1 to A4. Meaning this one measure the current here A1, measure the one in A2, measure the one in A3, and measure the one in A4 in amps. Okay, the currents are measured in amperes. This one is the short of ampere. Now, short form of ampere. Now, look at her results. She changes the number of cells and measures the current A1 to A4 in amps, and then look at her result. Let's take a look at her result. Now, number of cells. When she used one cell, this one means one cell. This one is just a cell. If you wanted 2 cells, it will be like this. Okay, it will be like this. This one means 2 cells. You can have 3 cells by adding another one long one, one short one. Okay, 2 from 2 is called battery. 2 cells is called equivalent to a battery, but 1 is just a cell. Okay, so for when she used 1 cell, the current A1 is equal to what? 0.4. Now you must check the value in A4. You know I said A1 and A4 has to be the same, because the current comes, get to junction X, split up, and then when they get to junction Y, they add up again. The one from this branch and the one from this branch, they sums up again. So the value of A1 usually equal to the value of A4. The value of A1 equal to the value of A4, right? So that's what you see here. A1 is 0.4 and A4 is also 0.4. When it gets here, it splits it to half. Here, they split equally, meaning the value of these bulbs are same. That's why the current splits equally to 0.2, 0.2. Okay? So here, when you increase the cell to 2 cells, the current flowing now is 0.6. So another 0.2 has been added to the previous 0.4. So when it gets to the junction X, it splits. 0.3 flow through that branch and 0.3 flow through the other branch A3. So A2, 0.3 flows through it, A3, 0.3 flows through it. So these are our values. Now, the question is, what do the result tells you about what happens in the current? What happens to the current in the circuit at point X and Y? At point X and Y. At point X, the current splits up. At point Y, they sums up again. At point X, the current splits up. At point Y, they sums up again. Okay? At point, so we say, at point X, at point X, look at point X. You know the current is coming like this. When you get to this junction, or at junction X, or at point X, the current splits into 2 equal parts. At point X, the current splits into 2 equal parts. Into 2 equal parts. Into 2 equal parts. Measured individually by ammeter A2 and A3. Measured separately. Measured separately. Measured separately by ammeter A2 by, okay, we can simply just write A2. We already know it's ammeter. By A2 and A3. Full stop. Then we say at junction Y, at Y, at Y, the current meets up again. The correct meet and sums up. The correct meet and sum up. The correct meet and sums up. The correct meets and sums up. So at this y, because the correct, the correct is a loop. It's flowing like this. You get to junction X, it breaks it to two. Part of the current goes through here, the other part goes through this other branch, and then these two currents they meet up here again, and then they continue their journey. So they sum up at Y, and then flow to this cell, and then flow to this, sums up, and flow to this cell, and flow to this cell, to this cell. Okay, so this is what it is. So we move on, we get 2 marks, 2 marks. We get 2 marks for doing this. The other one is the 2 marks for this one. You see, one of the results is anomalous. Circle the result in the table that is anomalous. Okay, the one that is different. Let's go to the one that is different. Okay, we can erase these ones because this one was just for teaching purpose. Now, they say one of the results didn't follow the pattern. Which one is that? Here is 1.8, here is 1.8, and it's split to 0.9, 0.9. So this one is okay. Okay, let's start from the top. 0.4 split to 0.2, 0.2, and then we get 0.4 back. Okay, so there was an increment of 0.2. 0.2 was now added after adding one cell, one more cell. We get 0.2 added to the original 0.4. So split, we get back at 0.6. Another 0.2 was added again after making a third cell. We split 0.4, 0.4, we get back at 0.8. So this is still following the same pattern. But from here, it didn't goes to 1.2, 1.0. 0.2 was supposed to be added. Here, 0.4 was now added. After we add another cell. Every time we add a cell, we are supposed to get additional 0.2. So here, it jumped to 0.4. Even though it splits, and you get 1.2 back, but there is something to note. So I think that's where the abnormality came. So here, you added one more. It was addition of 0.2. From 1.2 to 1.4, it split to 0.7. Okay, this is the big abnormality. So the current here and this one, way different. So this is the abnormality, not even in this place. Okay, because this abnormality is way bigger than it didn't sum up. The value of A1 should be the value of A4. So this is the abnormality. This one is same. The value of this is same as the value of this. So the abnormality is here. So they are asking us where is the abnormality in the table. They say we should circle it. So we already circled this one. This is the abnormality. So here you get 1 mark for noting this. Because it's different from your A1. A1 should be equivalent to A4. A1 should be equivalent to our A4. Our A1 should be equivalent to our A4. So you can see this one is not equivalent. A1 and A4, they are not equivalent. They are supposed to be same. This and this are supposed to be same. So this is the abnormality in the question. Now we go to the next one. It says predict the values of A A2, A3, and A4 if the value of A1 is 1.6. Predict. Okay? Okay, first and foremost, A1, A4, they are same value. So if A1 is 1.6, easy, we get the value of A4 will also be 1.6. So half of it, half of the value is ammeter 2, which is 0.8. If you divide 1.6 by 2, you get 0.8. So here is 0.8 ampere, and here also 0.8 ampere. Here also 0.8 ampere. So this one was easy to note. Why? Because you already know the pattern. If they give you 1.8, A1, A4 will also be what? 1.8. Then half of it is A2 and half of it is, the other half is A3. So that's what we did here. If they give you the value of A1, it will be the same value as A4 after the current meets up. A2 is the junction X where it splits, so half of it flows in that branch, and then the other half flows in the bottom branch. So this is it. We get this one, you get another 1 mark. Now question 10. Question 10, it says, Carlos investigate electrical resistance. Look at his circuit. You know electrical resistance? V, first of all, Ohm's law. In Ohm's law, V equals to IR. In Ohm's law. So R is the resistance. So R resistance is equal to the voltage over, make R the subject, divide both sides by I. So voltage over I. So this is the formula for resistance. This is the formula for resistance. This is I, okay? I means current. Current means I. That's the symbol for current. Okay? A is the ampere, the unit of current. I is the symbol, okay, of current. I know if you wondering current is C, starts with C. Why are we using I? Okay, that's the symbol that has been chosen to represent current. V is voltage. R is the resistance. So this is the formula for calculating resistance from Ohm's law. From Ohm's law, this is the formula for resistance, which is derived from here. Okay? Now, a voltmeter is always connected parallel to the resistor. This is a voltmeter. We always make the voltmeter, we always connect it parallel to the resistor. And we connect the ammeter, this ammeter, this A means ammeter, not the A for ampere. This A means ammeter. So we connect the ammeter in series. We connect it in series with the resistor. Series means both of them are in one loop. Both of them are in one loop. Okay? We connect the ammeter in series with the resistor, but we connect the voltmeter in parallel, like parallel. The voltmeter is here, the resistor is here. Now the reading on the ammeter is 0.6. That's the reading here. The reading on the ammeter is 0.6 ampere. Okay? 0.6 ampere. Now the reading on the voltmeter is 1.8. This is the voltmeter V. This voltmeter is not the voltage. Okay? The symbol for voltmeter, you draw a circle, you put a V inside, and then you show with a line like this on both sides. This is a voltmeter. Okay? It's different from voltage. Also, ammeter is different from what? It's different from ampere. If you are drawing ammeter, you draw a circle, you put A inside, and then you show with a line from both ends. This is an ammeter, this is a voltmeter. This is a symbol for, circuit symbol for ammeter, and this is a circuit symbol for voltmeter. Okay? So this is a voltmeter. The voltmeter is 1.8 volt. Volt is the unit of voltage. Now, calculate the resistance of the resistors, include the units. Now, they say we should calculate resistance. You remember, I've given you the resistance formula. Resistance is equal to V over I. Resistance, R, is equal to the voltage over the current. The voltage flowing over the current. This is physics also. So we say the voltage is 1.8 over 0.6. 1.8 over 0.6 ampere, the value of the current. So he said we should include the unit. So I put the unit here, 1.8 volts over 0.6 ampere. So this 1.8 divided by 0.6, this is 0.3, 0.3, 1.8 divided by 0 is 0.3 or 3, 0.6. What do we get? 3, right? So we get 3, not 0.3, we get 3. So our resistance is 3 ohms. The unit of resistance is ohms. This is the symbol for ohms. If you don't know, you learn it today. The symbol for the units of resistance is like this, ohms. This is how we draw it. 3 ohms. So you say the resistance of the resistor is 3. You write 3 here. And you put the unit. Unit is ohms. You draw the unit here, ohms. You get 2 marks for doing this. Now it says, Carlos replaces R with a resistor of greater resistance. Carlos replaces R, this R, with a resistor of greater resistance. What happens to the reading on the ammeter? You know, if you increase resistors, the value of the current goes down. They are inversely proportional. Look at the formula. Look at the formula. Resistors is inversely proportional to the current. Right? Resistor is inversely proportional to the current. If you look at it from the formula, R equals to V over I. They are inversely proportional. See? Inversely proportional. So if you increase the R, look at the question. Say Carlos replaces R with a resistor of greater resistance. Meaning you increase this value of R. What will happen to the current? Current will become smaller. What happens to the reading of the ammeter will be lowered. Okay, the reading of the ammeter will be lower or smaller. Some students can write lower, some might write smaller, and so on and so forth. Is that okay? So I think this is the end of this paper. So with yesterday and today, we finished the science. We merged it together. Okay, it's one class. Thank you very much. Thank you for joining us.